Hello again. So in this session, we are going to apply the Reynolds decomposition that we already applied to continuity equation to Navier Stokes equation. Okay, so let's remember what was the Navier Stokes equation. So here I'm going to write it again. Rho partial ui over partial t plus uj partial ui over partial xj. So this was like the left hand side and the right hand side we had the sum of the forces. So here I'm just writing the pressure and the contact forces or stresses in the flow, which was tau ij partial xj. Okay, so now let's we want to apply these Reynolds decompositions that we had here. So let me just copy them here. So I want to apply these here to this equation. So we have, instead of ui, I'm going to write this, the sum of the mean and the turbulent part. So we have rho, and then I am going to split that partial ui over partial t plus partial u prime I over partial t. And then the second term is going to be plus we have a lot of terms there, so let's look at that. So first one is going to be uj partial ui over partial xj. Then the second term is going to be uj prime partial ui prime over partial xj. Then the other terms will be the cross terms, which will be uj partial u prime I partial xj. And then the last term would be u prime j partial ui over partial xj. Okay, so these are all these terms. If you just use this decomposition, okay, I just expanded them here. Okay, so this equals to the right hand side, which is going to be minus partial capital P over partial xj minus partial P prime over partial xj plus partial tau ij over partial xj plus partial t tau ij prime over partial xj. Okay. Okay, so this is going to be the expanded form of the Navier-Stokes equation using Reynolds decomposition. And the other thing that we are going to do now is to take the average of this So if we take the average of it here for all the terms, the average of the whole equation, we know that some of the terms are going to cancel out. For example, this term, we know from past that is like this. We can just separate it, put the average inside the derivatives, all of the derivatives, and then this is like a fluctuation term. So this term is going to be 0. Similarly, this term is going to be 0, and this term is going to be 0. Okay? Now, how about these terms? This term is going to be also 0. Why? You can investigate it. Because this equals to, if we take the average of that, you can take this uj out of the average, and then you have the average of u prime I over partial xj, right? And this we know is 0. So this term is going to be also 0, and similarly this term, because the average of this, if you take that, is going to be the average of u prime j. We can take this out of the average because this is an average already. And we know that the average of this term is going to be 0. So these two terms are going to be also 0. So we are left with the following equation. Rho, the average of this is going to be itself because it's an average already, so it's going to be rho partial ui over partial t plus, we are going to also have these terms because this is also an average, it's not 0, and this one is a cross term, so we don't know exactly is it going to be 0 because it's multiplication of two terms, and we don't know, it's like a covariance as we discussed here. So we are going to have uj partial ui over partial xj plus u prime j partial u prime I over partial xj, and this is an average, so I just show it with bar. Also you can show it with like bracket. Again, these are the same thing, equals to the right hand side, which is going to be minus partial capital P over partial xj plus partial Tij over partial xj. And this is a very important equation. This is what we call RANS equation. Reynolds average Navier Stokes equation. It's very similar to the Navier Stokes, except if you compare these two, it's very similar to the original Navier Stokes equation, except we have an additional term here, this term, which is kind of the main difference with the original Navier Stokes equation. So this is the main difference, but the other terms are kind of similar to that. And now let's see what is this term. Let's look at this term and see what it is. So u prime j partial u prime I over partial xj bar, or let's say the average of that, I can write this as what? I can write this inside that. We know from, again, calculus that you can write this, the derivative of multiplication, u prime I prime u prime j prime over partial xj minus u prime I partial u prime j over partial xj, right? So this is from calculus. You know that, again, it's not necessarily this. Let's say partial uv over x equals to u partial v over partial x plus v partial u over partial x, right? So I use this. If we use this, you are going to get this identity here. So we can just rewrite it as this. And so let me just write it. So we can say that this equals to partial u prime I u prime j, say bar over partial xj minus u prime I partial u prime j over partial xj. Okay. So what is this? Let's look at our continuity equation here. Let me copy it here. This term says that this inside this average, this is going to be 0. This is what? This is the divergence of u prime. And we know that this is going to be 0. So you are multiplying 0 to all these variables and then take the average. So the result is going to be 0. So this is already 0. And so this equals to partial u prime. This is from continuity. U prime I, u prime j bar over partial xj. So this term actually equals to this. So I can just rewrite this equation again. Instead of this term, I can take this to the right-hand side of the equation. And we are going to figure out why we are doing this in a moment. So we have minus partial capital P over partial xi plus partial tij over partial xj minus, I took this to the right hand side. I take this to the right hand side, and instead of that I write this. As we know, this equals to that. So minus rho partial over partial, and this is x, partial x j of u prime I u prime j bar. Okay. So this equals to minus partial p over partial xi, and then if we factor partial over partial xj, we are going to have tij minus rho partial minus rho u prime I u prime j bar. Okay. Very interesting observation here that this additional term actually, if you look at it here, it acts like a stress. When you put it on the right hand side and then you have this partial over partial xj, this acts like a stress. And we call this actually Reynolds stress. So these are all Reynolds stresses. It is not really a stress. It's not really a stress, right? Fundamentally, it's not a stress. It's not really stress. But, and it comes from the nonlinearity of uj partial ui over partial xj, right? It comes from the nonlinearity of this. It's not really a stress, but it acts like a stress. So that's why we call it Reynolds stress, okay? So again, Tij is molecular diffusion of momentum. This is a real stress. And u prime I, u prime j bar is transport of momentum due to the fluctuations. Okay, so there is a big difference between them, but rho ui prime j prime actually acts like a stress in a flow. Okay, so let's take a deeper look and more careful look at this term ui prime uj prime, and let's see what it is actually, this tensor. So this tensor, if you want to write it down, u prime I, uj prime, the whole matrix of that for 3 velocity, because we have 3 velocities, right? 3 components of the velocity look like this. So the first one is u prime 1, u prime 1. Second one is u prime 1, u prime 2. Third one is u prime 1, u prime 3. Second row is going to be u prime 2, u prime 1. U prime 2, u prime 2, u prime 3, 2, u prime 3, and the last row is going to be u prime 3, u prime 1, u prime 3, u prime 2, and u prime 3, u prime 3. Okay, so this is the all the elements of this tensor, and we know that xy bar equals to yx bar. There is a symmetry here. So the only unknowns of this matrix is going to be u prime I, u prime j. If we know 6 components of that, which are u prime 1, u prime 1, u prime 2, u prime 2 bar, u prime 3, u prime 3 bar, u prime 1, u prime 2 bar, u prime 1, u prime 3 bar, and u prime 2, u prime 3 bar. If we know these 6 components, then the other 3 will be known because of this symmetry, okay? Well, it can be determined based on this symmetry. So in total, we have 6 unknowns that we don't know. What are they? We don't really know them. We know that these are actually flow dependent. They really are different, and each flow in different flows, like if you have a vortex, if you have a boundary layer, all of these can actually impact these Reynolds stresses. Okay. On the other hand, we only have 4 equations, which are 3 momentum equation in x, y, and z direction, and 1 continuity equation. we face a problem here. The number, as you see, the number of unknowns in the set of equations for turbulent flows is larger than the number of equations right? We have 6 unknowns, it's more than the number of equations that we have, and this is called closure problem. We cannot really close these equations with these unknowns, with these number of equations. So we need to define new equations. In other words, we must parameterize the turbulent fluxes in order to be able to close the equation. So we need to add and define some approximate equations to kind of approximate these unknowns based on the known variables like U, V, W, these kind of variables that we know, okay? And relate them to the variables in the flow field, okay? So there are many different parameterizations for these Reynolds stresses, right? We can relate them to a lot of different type of flow parameters with different approximations and different models. Here, I'm just only giving you one of the simplest ones and one of the most widely used parameterizations, which is known as first order local closure model, or K theory. So it's the first order and it's a local closure, meaning that we just relate the Reynolds stresses to the variations in that specific location, right? So it's a local thing. We don't want to say if you have a flow here, you want to calculate Reynolds stress here, you don't want to relate it to here, somewhere here, okay? So that's called, it can affect actually in the turbulent flow, like far field can also affect that, but that kind of parameterization is called non-local parameterization, but the local one is you just look at the flow around it to approximate these kind of Reynolds stresses, okay? So the first parameterization that I'm going to introduce is a first order closure. Again, you can have higher order closures, but the simple one is the first order. So in this parameterization, we just say U prime J and say epsilon prime. Epsilon can be anything. It's not just velocity. Mostly we use it as velocity, but it can also be heat or moisture or anything. So this turbulent flux, we can just approximate it with a constant K minus K times partial epsilon bar over partial xj, okay? So we can approximate it with a mean variable. So this is known as local closure. As you see, this is a mean variable, an average variable. So We can approximate these turbulent fluctuations with this mean average variable, okay? What is K? K is a scalar with a unit meter square over second, which is also called eddy viscosity or diffusivity. And U prime J, Kc prime, is just turbulent fluxes. And again, you can guess why this is called eddy diffusivity, because if you have this equation, so let me just write this one, this term of that. So if you remember from when we drive the Navier-Stokes equations, we wrote this in terms of mu, right? So it was this one, the left one, we can write it in terms of the eddy viscosity, so it's going to be mu grad square. Let me write it in terms of in the index notation is going to be mu partial square ui over partial xj. This is the first term, okay? And then for the second term, you can write this in terms of this k, okay? So we are going to have minus, and say k is constant, you can take it out of the gradient, so we are going to have, this was j square, we're going to have plus k partial square of ui over partial xj square. You can just substitute it here. And so as you see, and then we have a row here. So this k is actually behaving like eddy viscosity, right? These two is like viscosity, it behaves like viscosity, okay? And we call that eddy viscosity or turbulent viscosity, right? Because this is a viscosity that comes from turbulence, and this is a viscosity that's due to molecular diffusion, okay? So that's why I just want to say why we call this eddy diffusivity or eddy viscosity, okay? So now let's go back. This closure approximation is called K-theory or gradient transport theory. It's one of the simplest closures, okay? And for example, so some examples of that. Say for just velocity, if you want to say velocity, u prime 3, u prime 1, this equals to u prime 1, u prime 3, right, from symmetry. And this will be minus k partial u bar 1 over partial x3. Or you can write it in this way, u prime w prime. Let me write it this the other way. W prime u prime equals to u prime w prime equals to minus k partial u bar over partial z. Okay, again, u1, u2, u3 can be like u, v, w, and x1, x2, x3 can be x, y, z. Okay? But this relation is also valid not just for velocities, but also for heat and moisture. So for moisture and heat, we'll use, instead of K, we just use KH for heat and KE for moisture. And we know that in neutral conditions, there is a relation between KH, KE, and K from momentum. And that is KH equals to almost KE and equals to about 135 of Km or momentum. These are for momentum, right? And these are for heat. So for example, we can write, instead of U, we can write W prime theta prime, where theta is temperature, equals to minus KH partial theta bar over partial Z. Again, this is to show that this is also valid for scalars like moisture and heat, these first order closure model, right? We can use it for moisture and heat as well. And this is going to be how it would look like, but we need to use a different K or a different eddy viscosity. It's not going to be called anymore eddy viscosity. It's thermal diffusivity right now, because we have it for temperature. But again, we can use a similar closure for closing the temperature fluxes or moisture fluxes the same way that we are using this. But remember, this is an approximation. This is not a general rule. It can be really different for any flows, and it might not be necessarily valid in all cases. But this is the only way we can close the equations. So we need to add parameterizations for the turbulent flux, and this is a first order closure. We can actually go beyond that and go solve more equations, add more equations to actually solve these fluxes, okay? But this was one of the simple ways. Okay, so let me review what we learned today. So we started first about Reynolds decomposition. So we talked about mean, what is mean, and what is fluctuations part. We talked about Reynolds decompositions. And then we defined these rules that are valid for Reynolds decompositions. And then we applied the Reynolds decomposition to the continuity equation, and we got these two formulas that the divergence of the fluctuation part and the mean part is going to be 0. Okay. And let me see here. I think, let me see something here. Yeah, I think I need a index here. I think I forgot to add that, so let me add it here. It's for all velocities. Yeah, so we have this, and then again, Reynolds average continuity equation. So we showed that the divergence of the fluctuation part and the divergence of the mean part of the flow should be 0. Okay. And after that, after this, we talked about Reynolds average Navier Stokes equation. So similar to the continuity equation where we applied the Reynolds decomposition, we applied the Reynolds decomposition to the Navier Stokes equation, and this was what we got. And this is the only additional term compared to the original Navier Stokes equation. And then we showed that this equals to this term, and this term, we showed that this actually acts like a stress, and we call that Reynolds stress. Okay. And we found that we have 6 unknowns of this, so we need to add more, but we have 4 equations, so we need to add more equations in order to be able to close the system of turbulent equations. So we faced with closure problems, so we talked about closure problem. And finally, we define these first order local closures, which are kind of one way, an approximation, a closure approximation, or K-theory, or gradient transfer theory that can actually close these equations. And we showed it for different kind and how this looks like. Thank you very much, everyone.